Hi guys, and welcome to our 10th lecture in OFDM-MIMO. What I want to do today is actually split into two parts. I want to discuss some more advanced topics about OFDM. Naturally, this is going to be a continuation of our previous OFDM lecture, but I'm going to do something additional. And this is I'm going to give what I think is a unique perspective into some of the most important points about OFDM. So let's just get started. I want to start with a different view, a different direction of looking into the cyclic prefix. Okay, so in the previous lecture we took the classical approach, and we discussed that the role of the cyclic prefix is simply to make sure that the linear convolution that the channel does, it transformed into a circular convolution. But now I want to take a different direction. I want to take a look at the continuous time signal. So you can agree with me that this would be the OFDM signal. But the most important part in this discussion is taking a look at the time intervals on which I'm considering the waveform. So now I'm considering the OFDM signal for t from t, the OFDM symbol duration, to minus t guard. Okay, so if I'm just taking a look at the picture, it's from t, from here, to minus t guard here. And actually, because all of the sine waves that make up the OFDM signals, all these guys are periodic, I can simply write the same expression but extend it to minus t guard. And actually, this would be a cyclic extension of the signal. So I'm considering the OFDM symbol, but I'm considering this expression from minus t guard up to the time interval t. And I'm taking now this OFDM symbol and convolving it, passing it through a convolutional channel. In this discussion, beta I would be the complex valued attenuation corresponding to the ith path. Okay. So I want to take a look at what happens for this OFDM signal, a symbol, a symbol, and what happens when this guy is propagating through the LTI system. Okay. So, and again, the most important part is to take a look at the time intervals on which I'm considering the waveform. So, for tau I smaller than the CP length, the guard time interval length, and for t between 0 and t, we have, and this is the key point, I'm observing the signal only from here to here. This is the FFT period. I'm looking at it only at this time. Moreover, I'm assuming that the maximal delay of the channel is smaller than T guard. So if I'm trying to portray this situation on the left-hand side, so this would be the guy with 0 delay. And this would be a delayed version. This would be one delay, and this would be the second delay. But you see that actually the two delays that I have, they are both smaller than the cyclic prefix length, so that within this interval, within this interval 0 to t, the equation holds. The equation for the OFDM symbol holds. In contrast, let's take a look at a different situation. This would be 0 delay. This would be tau 1 that is smaller than Tg. And this would be another tau that actually is larger than Tg. So you can see that in this period, this interval, the equation doesn't hold. Yeah? So in the blue one, the blue reflection. So assuming that we're looking at the signal from 0 to capital T on the OFDM symbol duration, and assuming that we are on this part, this actually corresponds to this situation, meaning that all of the reflections are within TG, within the cyclic prefix duration, then we can write this equation. And again, the key point that this equation holds only for the conditions that I just mentioned. Okay. So if this equation holds for yt, the received signal, then of course, the first thing that I would do is just exchange the summation order. Yeah. AK, of course, does not depend on I, so it can stay outside. But let's see, what is this guy? What is this guy? We have sum beta I e to the minus j, and I remind you, e to the minus j 2 pi f tau I, this would be h of f, right? So this guy is simply the Fourier transform of the impulse response of the channel, meaning the frequency response of the channel, HF, evaluated at the point k over t. So actually, this is another way to prove what we saw in the previous lecture about the circular convolution. But I think this is a more instrumental way to look at it. Think about it like that. The received signal holds subcarriers AK and at the subcarrier frequency k over t. But now, instead of like receiving AK modulating the k over t subcarrier, what I have is AK times HK over t modulating the k subcarrier. Okay, it's like instead of transmitting AK, like I transmitted AK times HK over t. So naturally, at the FFT output, if I'm just projecting everything on the complex exponential, yeah, this would be the FFT output. Because the FFT would coincide with the Fourier transform on the interval from 0 to t. This is from Nyquist. So at the FFT output, I would simply have the transmitted QAM multiplying the response of the channel exactly at the subcarrier frequency. So this is like a different way to look at the role of the cyclic prefix. So now, taking a look at this from this perspective, I'm asking you, is this surprising? Is this surprising? I think that when you take a look at OFDM from this specific perspective, actually you can understand OFDM totally from basic principles, meaning basic principles of like a second year of undergraduate studies. So let's take a look at that.